So, this is a switching topic we are discussing last class. This circuit we have discussed in the last class. This is a common emitter configuration circuit, uh, which is in normal active mode. Okay, the meaning of this normal active mode is this emitter base junction is forward biased, whereas a collector base junction which is reverse biased. Okay, so this is normal active mode. And here we have a supply voltage. You can see that input signal is a pulse waveform which is varying uh, to the reason why we apply here pulse, because this waveform looks like a pulse which has low value, and you can see all the way it goes to high 10 volts, and it remains 10 volts for some time duration, and again it falls back to minus 10 volts here. So, this kind of pulse waveform is applied at the input of this. Uh, okay, so we can bias this emitter base junction under different biasing conditions. So, low voltage here corresponds to cutoff region and high voltage corresponds to saturation region here. So, to observe how the circuit performs for cutoff region and saturation region, we applied a pulse waveform of this sort. Last class we have seen the characteristics plotted for this circuit, which is shown here. Uh, Here there are two things one need to observe. One is normal device characteristics, output characteristics, what you are seeing here. So, this is a graph of collector emitter voltage versus collector current, which is in milliampere for constant base current. So, the transistor, when you connect in common emitter mode, the output voltage and current will follow this characteristic here. Okay. On top of this, what you see is a straight line here, which is having a negative slope, okay, which you are observing here. This is a straight line, and where do we get this straight line? So, this straight line you can obtain it by applying KVL to this loop. So, if you apply Kirchhoff voltage law to this loop, this is a loop even here, this is a loop. In this way you can apply Kirchhoff voltage law. So, you will get a KVL equation for this. You can consider this as supply voltage as battery as VCC, since it is connected to the collector, and this resistance you can take it as can consider as RC. Now, if you apply KVL in this loop, so starting from this battery connected here VCC 40 volts, so then you can arrive at KVL equation. So, KVL equation is minus VCC plus this voltage across this collector and emitter of a transistor when we are moving in this path. So, the voltage here is VCE. So, plus VCE. So, that is the voltage across collector and emitter of a transistor, and when we pass on through this loop, we have a resistance of 5 kilo ohm. So, current through this resistance is IC, and the resistance value is RC. So, therefore, we can write this as plus IC times RC. So, this is equal to 0. So, this is the KVL equation. So, this is obtained by applying Kirchhoff voltage law to collector emitter loop. So, you can simplify this equation for collector current here. The reason is already you have a device characteristic for VC versus IC. Now, let us write this equation in terms of IC. So, when you write this IC equation here, we write here, this is this implies IC, which is equal to minus 1 by RC times VCC plus VCE by RC. Okay. So, after simplification you get, this is a standard form of equation. So, this equation resembles a straight line equation like y is equal to mx plus c, where y is equal to IC. Okay. So, y which is equal to IC, and M slope is equivalent to minus 1 over RC. M slope is minus 1 over RC, and y intercept here is VCC by RC. Therefore, C y intercept, which is equal to VCC over RC. So, this is a straight line. Now, to draw this line on this characteristic, we need to have 2 points, which you can see here already identified here. One is C point, other one is S point. So, how do we obtain this C and S point using this equation? So, C point can be obtained. C is nothing but a point on the x axis, can be obtained by making IC as 0, y value as 0. So, y is nothing but IC here. So, if you do that, the value coordinate value for C is now, which is equal to this is a cutoff region C. Do not get confused with this C and this C. This is y intercept C, this is the cutoff region C. So, C is given by now the value, it has got x value, x is nothing but which is VCC, which is 40 volts. So, it has got x value as VCC, but y value is going to be 0. So, y value is going to be 0. Even if you substitute this y IC as 0 in this equation, so this equation will go off and RC cancel and VC will be equal to VCC. So, we can obtain from this C point by substituting IC as 0 in this equation. So, this is under the condition IC equals 0. Next is you can also obtain similarly the S point, this point here, by making VCE as 0. So, because when you end up with on y axis, the x will be 0. So, when VCE is 0, and you can obtain the value of IC. Substitute here VCE as 0. So, you will get a value of IC as minus VCC by RC. Okay. So, can if you substitute IC 0, if you transfer to other side, it will be, you can see this value, let me write here. So, this value is x is 0. So, x is 0, x means it is, in this case it is VCE. So, x is 0, we see this is 0, and you can obtain here value of IC. So, IC is nothing but which is VCC by RC here. So, this is VCC by RC. So, this is with condition VCE equals 0. Okay. Sorry. Just yeah, this is VC equals 0 value here. Okay. So, this value is going to be 0 here. Okay. So, we know 2 points now, C and S. You can just locate these points here. One is going to be with VCE, and this is 0 VCC comma 0, and this point is going to be 0 comma VCC by RC here. So, having these 2 points, you can join these two line, this point and make a straight line, and this line is going to be called as load line here, because slope of this line is equal to minus 1 over RC. So, this is called as load line, and the slope of this line is minus 1 by RC. So, we have shown already slope is minus m, m is nothing but slope, which is minus 1 over RC. The reason why we have drawn on the output characteristics, reason is because this x and y values of this straight line and x and y values of the device characteristics are same. So, therefore, we have superimposed this load line on this characteristics, and you can make a lot of analysis on this load line on the characteristics. One simple way is for each and every base current here, you can identify the value of collector emitter voltage and collector current. For example, if IB value is say 0.02 milliampere, so the load line and characteristic curve intersect here, and if you just draw the vertically line downwards, you get a VCE value as 30 volts approximately, and if you extend this to the y axis, the collector current is going to be 2 milliampere. So, that means you can obtain the value of VC and IC corresponding to this intersection. Similarly, if you increase base current to 0.04 milliampere, the load line intersect with the characteristic here, and now you can see that vertically if you draw a line, the VC value is 20 volts and IC is going to be 4 milliampere. So, that means as you keep on moving for larger base currents here, higher values of base currents, the collector emitter voltage keeps decreasing. So, collector emitter voltage is nothing but voltage between the base and the collector here. So, voltage across transistor gets decreased as you keep increasing the base current here. Okay, where exactly that voltage is moving? That complete drop moves to the external resistor here 5 kilo ohm. Okay. So, drop across this external resistor 5 kilo ohm and the drop across the transistor should be equal to 40 volts. Now, here when this input base current is 0, when the base current is 0 here on the x axis here, there is no base current now. Complete voltage at the collector and emitter is 40 volts. So, that means voltage, the entire 40 volts what we applied, that is dropped across this. Since once you make base current as 0, this when you make a base current as 0, collector current also becomes 0. So, there is no drop across this. So, voltage drop across this is going to become 0. So, therefore, the complete voltage 40 volts will be dropped across BJT, collector emitter particularly. And as you keep increasing the base current, so instead of making this base current not equal to 0, if you keep increasing the base current here, then the corresponding collector current increases. So, that is what you have observed here. As you keep increasing the base current, collector current also keeps increasing. So, now the collector emitter voltage keeps decreasing. As we have seen here, for 0.04 milliampere of base current, the collector current is 4 milliampere and collector emitter voltage is 20. Similarly, if you move to the higher value of base current 0.06 milliampere of base current, collector current is 6 milliampere, collector emitter voltage is approximately equal to 10 volts. You can see if you bring this line vertically downwards, it is 10 volts. That means across the transistor 10 volt drop is happening and remaining 30 volts is getting dropped across the 5 kilo ohm resistor, because at this point 6 milliampere is the collector emitter current, 6 into 5 becomes 30 volts. So, 30 volts will drop across the 5 kilo ohm resistor here. And lastly, at saturation point you can see S stands here saturation, and this at this point the base current is 0.08 milliampere. So, for this base current collector emitter voltage is close to 0. So, that means collector emitter across a transistor there is no drop. So, now 40 volts completely will be dropping across this 5 kilo ohm resistor. So, 8 milliampere is the current collector current, 8 into 5 kilo ohm becomes 40 volts. So, there is no drop across the transistor. That means the transistor is not consuming any voltage. So, entire the transistor is acting like a short circuit. So, this condition is called saturation condition. Okay. So, the point is located here. So, now it requires for us to understand the cutoff region and saturation region. Cutoff region where collector current is 0 and base current is 0. So, collector emitter voltage is 40 volts, whereas in saturation point the base current is 0.08 milliampere, that is very high base current, and the collector current is 8 milliampere, collector emitter voltage is 0. That means the complete transistor there is no drop across the transistor, and the drop has shifted to the external resistor 5 kilo ohm now. Okay. So, this is what the things we need to analyze here. So, now in an electronic systems like microprocessor, we need to operate between these two states, because usually in microprocessor the transistor functions like a switch. Okay. So, it needs to operate in off state, means we need to move into the cutoff region. On state means it is saturation region. That means we come across a situation wherein which we need to move from cutoff to saturation, saturation to cutoff many times, millions and billions of times within a given span of time here. Okay. Now, question rises here, how much time the device is going to take, transistor is going to take to move from saturation to cutoff, and cutoff to saturation. These are the performance of a system depends upon. Now, how fast we move, depending upon that the microprocessor speed is depends upon. Okay. The switching between the saturation to cutoff or cutoff to the saturation, if it is faster, then definitely the microprocessor also will work faster here. Now, practically speaking, there is some time the BJT will take, okay, to switch between cutoff to saturation and saturation to cutoff. Now, let us analyze, understand these the timing instances here. Okay. Uh, Now we have seen these various modes of operation. So, for the device to work like a switch, we need to operate in saturation region. This is the saturation region where emitter base junction, emitter base junction, collector base junction both are forward biased, and in the cutoff region both are reverse biased. So, cutoff region offers high impedance state, whereas forward bias or for active the saturation region offers low impedance state. So, these two regions, the switching between these two, okay, is nothing but you are making device to operate in cutoff region and saturation region respectively. And we do not operate device in the inverted mode, but this is not used here in any application, but this is normal active mode is the most widely used mode when we use BJT as a amplifier. Okay. And whereas in cutoff and saturation mode is used when we want to use BJT as a switch. So, it will act like a half switch here, and whereas in the saturation mode it will act like a on switch here. So, this we have discussed already with reference to load line here, and same thing with reference to mode of operation, we need to switch between cutoff and saturation frequently here. So, these things we have seen with reference to the cutoff region. We will straight away move into the switching cycle now. Okay. Switching cycle, the saturation here. Now, here we need to understand the beginning of saturation and over saturation. So, these two things we need to analyze here. Now, let us try to understand this graph here. So, here this vertical line indicates it is a edge of emitter junction. So, this vertical line here, okay, so this is the edge of emitter junction. So, if you draw a line here, this is the edge of emitter base junction. This line indicates it is a edge of collector base junction, and this 0 is nothing but corresponds to this xn distance we are measuring from emitter junction to all the way to the collector base junction here. So, at emitter base junction xn is equal to 0, at collector base junction xn will be equal to WB. So, WB is nothing but which is the width of the base. Now, we can show the distribution of excess carriers, excess holes here. So, the excess holes on the emitter base junction, excess holes at the collector base junction here. So, excess holes at the emitter base junction is given by this equation. So, this is nothing but excess holes at emitter junction, emitter base junction, which is given by delta P. Okay. So, given by this P n times e to the power of q v b by k T minus 1. This is the equation for excess holes at the emitter base junction. Now, you can see this V b, which is forward biased for the emitter base junction, and so therefore, this is going to be a positive. Okay. So, forward bias means in large value, large voltage will exist at V b. So, e to the power of large value. So, definitely total value becomes very large. So, the 1 can be neglected here. So, this value, this equation can be approximated to P n times e to the power of q V b by k T. Okay. So, this is the equation for the excess holes at emitter base junction. So, this is shown as this height here, you can see here. So, the excess holes distribution at emitter base junction is this complete distance here from here to here. So, this indicates excess hole distribution delta P, which is given by this mathematical equation here. Okay. Now, let us see the other thing here. At the beginning of saturation means we have a positive emitter base voltage and 0 collector base voltage. Okay. Let us see now for 0 collector base voltage the excess hole distribution at the collector base junction here. So, the mathematical equation for excess hole, similar lines we can also write excess holes at the collector junction as delta P c. Now, delta P c depends on V c b instead of V b. So, V c b here by k T minus 1. So, here you can see that to commence the saturation we are going to make V c b as 0. So, once you substitute V c b as 0 here, so this V c b value becomes 0 here, total value exponential value becomes 1 e to the power of 0. So, this 1 cancels with this. So, delta P c is going to become 0. So, the delta P c, this value is going to become 0 here. So, what do we mean by that? So, when we want to operate the BJT in saturation, we need to apply a positive emitter base voltage, and if you make just a VCB as 0, so the saturation region will commence here. So, VCB is equal to 0 means the whole dense excess hole concentration at collector base junction. This is the collector base junction. So, the delta VCB is equal to be 0 here. So, here we have delta PC is going to be 0. So, here the saturation commences here. So, this is shown by the line here. You can see the hole distribution has been, excess hole distribution has been shown here. It is delta P at emitter base junction, and it is going to be 0 at the collector base junction here. Okay. So, this is the commencement of saturation here. Let me call this BOS, beginning of saturation. This line here indicates it is beginning of saturation. Okay. Okay. All right, now let us see that's various points to be covered here. So, now when the under this condition collector emitter voltage is going to be very small. Okay. So, the collector current is going to be the supply voltage. We have taken here example in our example we have shown here. Supply voltage is going to be 40 volts by 5 kilo ohm. So, under saturation 40 volts by 5 kilo ohm, you know that its value is going to be 8 milliampere. So, 8 milliampere current it will result here. So, this is the current flowing under the saturation condition here, 8 milliampere. Okay. So, so VC is going to be very small, because as I told already, in the saturation condition here the collector emitter voltage is going to be very small, and complete voltage drop occurs across the 5 kilo ohm resistor. Okay. Saturation regime begins when the reverse bias across the collector junction is reduced to 0. So, that is what we have shown here. When the reverse voltage is reduced to 0 and there is a positive emitter base voltage, this is the beginning of saturation here. Now, let us see that what happens when we apply the excess voltage or higher voltage at the collector base junction, that to forward voltage. We should not apply negative voltage here, because we are operating BJT in the saturation. For saturation, emitter base junction should be forward biased, also collector base junction should be forward biased. So, here we started with making collector base junction as 0 initially, that is the commencement of saturation. Now, let us see when the collector base junction is forward biased. Okay. So, saturation continues as the collector becomes forward biased. Saturation will be further, it will progress when we when we apply forward bias. So, we have seen earlier with collector base junction as 0, but now we will see what happens when the forward bias voltage is maintained at the collector and base. Again, reconsider the same equation here, delta PC equation here. So, which is equal to Pn times e to the power of q VCB by kT minus 1. So, now this quantity is going to be positive. So, this is forward biased. So, therefore, this value is going to be large now. So, e to the power of large quantity becomes very much larger than the unity. This one can be neglected now. So, this approximately becomes equal to Pn times e to the power of q VCB by kT. Okay. So, this is the equation for the excess hole concentration at the collector base junction here. So, VCB is forward bias, delta PC is now a positive value. So, now we can show here in the graph. Now, you have seen already this graph above. So, this is the graph you have seen for the commencement of saturation. So, this is the beginning of this arrow mark is shown for the beginning of saturation. This is beginning of saturation BOS, and if you apply PC, delta PC by forward biasing the collector base junction. So, you can see that this is the excess hole concentration at the collector base junction here. So, now you can see that device has commenced saturation at this particular point here, and now because of larger collector base voltage applied. So, this has become now over saturated here. Okay. So, this is the over saturation. This all this region here, what you are seeing here is the over saturation region here. Okay. So, this is very important for you to understand, students. So, you need to know when the saturation commences, for what condition saturation commences, and when we apply voltage, how exactly saturation will become over saturation here. Under over saturation, do not think that the collector current increases sharply, but under over saturation condition, instead of collector current increase abnormally, it maintains a constant here. This is explained very well in coupled diode model. Just look at the coupled diode model, you will get to know the why exactly the current is constant, even though device is over saturated. Okay. So, that need to be understood here, because the emitter is also injecting the charge carriers, collector also it is injecting the charge carriers. So, therefore, you can see that the base, if it is lightly doped, then definitely small base current will result, but collector current is maintained constant here. Okay. So, collector current will not increase due to the increase in the base current here. Okay. Load line already we have shown, we have discussed about that, that is drawn by having with the battery of 40 volts and 5 kilo ohm resistor, you can draw the load line. So, load line graph we have shown already with battery of 40 volts and 5 kilo ohm, we can draw this load line. This is the equation we obtained by applying KVL, and we got 2 points and we combined this and we are superimposed on the output characteristics. Okay. Now, we will see that other timing things here. Saturation is reached by increasing the base current, we have seen that. So, if you increase the base current, the base emitter by increasing the base emitter voltage and even applying the collector emitter voltage, you are in the over saturation mode. So, it is the beginning of saturation, and this line indicates it is final stage of the saturation. Okay. So, this indicates the concentration of holes here. Okay. Now, it is delta P is here because of over excess voltage VB applied here, and this is the delta PC value here. Okay. With VCB is equal to 0, the delta PC will be 0. So, here, so delta PC is going to be 0 at this point. Okay, at this exactly at this point here. Okay, so the degree of oversaturation does not affect the value of IC significantly. Do not think that IC value will be affected significantly by with the value of oversaturation here. Now, let us analyze the time required for to switch between the one state to the other state here. Okay, so it is very important for us here. Okay, one state to another state means we are looking basically time required to switch the transistor from cutoff region all the way to saturation region. How much time the device takes, let us analyze that. Okay, so turn off time also we should know. Turn off time means it is a time for a transistor to switch from saturation to cutoff. So, these two turn off time and turn on time, this is called as a turn on time. These two timings are very important. Okay. So, usually if you look at a bipolar junction transistor, the turn off time is longer for larger values of the stored charges in the base compared to the turn on time. Generally, we think that turn on time is larger, but in fact, in BJT with reference to BJT, turn off time is longer compared to the turn on time. We will get to know all those things when we look at the switching cycle. So, we understood now what is turn on time, what is turn off time. Turn on time means it is changing of the BJT from the state of cutoff to saturation state. Turn off time means the BJT changes its state from saturation to cutoff. So, it is vice versa, just opposite of the turn on time is turn off time here. Okay. Now, let us see the switching cycle here. This is very important to understand when we use BJT in switching applications, especially in digital circuits. So, one need to understand the switching cycle here. Various mechanisms of switching cycle are illustrated in the figure 7.15. 7.15 figure is shown here for your reference here. So, this is the figure 7.15 which you can see here. Okay. So, these things already we explained here. So, this is beginning of saturation, this is the shaded portion indicates it is oversaturated here. Now, let us mainly focus on this switching effects in a common emitter transistor circuit. The figure A shows the circuit diagram for the common emitter configuration, and here you can see that we apply a pulse waveform as an input for this common emitter configuration circuit here. So, the reason why we apply pulse waveform is because we need to switch its state from cutoff to saturation and saturation to cutoff. So, here if you apply the pulse waveform like this, so this is usually BJT will be in the cutoff, and when you go apply a positive going pulse like this. Okay, so, from negative to positive going pulse. So, here the BJT moves into the saturation. Okay, saturation here, and here BJT will be in the cutoff. That is the reason for applying this pulse waveform as an input for this common emitter circuit here. So, that has been shown here the base current, the way we apply the base current here. So, that is shown with this the waveform here. This is the base current waveform which is applied here, which is though do not worry about direction of the base current here. So, though as per the transistor this directions has been shown here, but this is the waveform base current waveform which is given here. Initially we start with cutoff region and then move suddenly all of a sudden to cutoff to saturation, and then from saturation to the cutoff here. So, here the initially we start here with cutoff. Let me show cutoff as C and saturation, and again we are in the cutoff. And with reference to this switching states from cutoff to saturation and saturation to cutoff, let us see what is happening within the transistor, okay, and how much time the transistor takes to switch from cutoff to saturation and saturation to cutoff, that we will analyze step by step. Okay. I hope you understood this. This is a common emitter configuration circuit with the input as a pulse waveform what we have applied here. And here the figure B, what you are seeing here, it is an approximate hole distributions in the base during the switching from cutoff to saturation here. So, we know that various timings here, T naught indicates the cutoff. So, this is the T naught, you can see this under T naught, there is no hole distribution, which is a cutoff here. We do not apply voltage between the emitter and base, and collector and base, both are reverse biased. So, you can see that there is no hole excess hole density on both the emitter base junction and the collector base junction. So, this is an emitter base junction, edge of emitter base junction, and this line, vertical line here. So, this indicates collector base junction here, collector base junction here, and this complete region is the base region here. Okay. So, T naught indicates it is the cutoff region, timing for the cutoff region, it is whole distribution especially, and this is the whole distribution for the cutoff region, and for the whole distribution for the normal active is this much. This is the graph that shows whole distribution normal active. So, normal active region T1 indicates the whole distribution, and TS here. Okay, so, this TS indicates it is the whole distribution for the beginning of the saturation here. So, you can see beginning of saturation, and lastly we have T2, which is nothing but whole distribution at the final saturated state here. Okay. So, now you can see that we want to show here the value of delta P. So, delta P equation we already aware, again and again, see we keep repeating this equation. I suggest students to remember these equations, are very important to understand these graphs here. So, delta P is equal to P n into e to the power of Q times V B by K T minus 1. Okay, so this is the excess hole distribution at the emitter junction, and excess hole distribution at the collector junction is given by P n times e to the power of Q V C B by K T minus 1. This is the excess hole distribution at the collector base junction now. Now, you can observe here under the cutoff here, both will be equal to the minus, this is minus 1 here, I forgot to write 1 here. Okay, so this is 1 here. Okay, so I am sorry for this. Okay. Okay, so we have 1 here, and I will put a bracket adjacent to this. Okay, right. So, this is a delta P. So, delta P, this height you can see delta P keeps changing under the different modes here. You can see this is delta P and this is delta P. Again here we have different values here. First note under T naught, this is delta P. Okay, so here this is going to be the cutoff region. This is a delta P under the cutoff region, and delta P you can see that has been increased excess hole distribution in the normal active region. Normal active means emitter junction is here, normal active means emitter base junction is forward biased, collector base junction is reverse biased. Okay, so you can observe the further T1, since collector base junction is reverse biased, so you have negative value of P n. Okay, all this can be approximated using these two equations here. So, under reverse bias, you know that delta P, and let me write it here adjacent to this itself, so that you can easily understand. Yeah. Okay, I'm sorry, I have removed that. Okay. Okay, let me rewrite once again here. So, this is emitter base junction for normal active here. Emitter base junction is reverse biased, collector base junction is also reverse biased. Now, what will happen to the delta P? Just we observe it. Substitute here negative, because VEB will be negative for reverse bias, VCB also will be negative. So, therefore, this delta P will be equal to approximately equal to minus P n. This we have seen in cutoff region operation. Delta PC also will be equal to minus P n. That is why you see here negative region below this, negative. This is a T naught corresponds to cutoff region. Next, normal active region, emitter base junction is forward biased, collector base junction is reverse biased, delta PE is now equals, you can see this equation, this is positive, this value becomes very large compared to 1. So, now this value will be equal to Pn times e to the power of q v b by k t. Let us ignore 1 here. Okay, 1 becomes very small for large value of V E B. So, what about delta P C? Delta P C is again remains as minus P n. So, since it is reverse biased, delta P C remains as minus P n. So, here V C B is negative, and so therefore, this P n negative or even 0 also. So, delta P C either it becomes 0 or minus P n. For V E B negative, it becomes minus P n. For V E B 0, V E B 0, it becomes 0. Delta P C, it can have these two values. Even here also, it can be 0 or it can be minus P n. It all depends on what voltage we apply at collector and base. Next, beginning of saturation, we have seen that beginning of saturation is again for this emitter base junction is forward biased. I am sorry for that, forward biased, and collector base junction is 0. So, we have seen that delta P, okay, you can see that which is equal to P n times e to the power of q v b by k t, same equation once again, but delta P C is equal to 0. Okay. So, that is for the beginning of saturation for this region here T T S. So, here, okay. So, this is a T S, beginning of saturation here. Next, we have lastly final saturated or oversaturated. So, emitter base junction is forward biased, collector base junction also forward biased, and delta P E will be same as this, delta P C also will be P n into e to the power of q v c b by k t. Okay, so, this is the value. So, even we have a small value of delta P C. So, this is delta P C. So, this is oversaturation. We have seen this already. Okay, so, this is oversaturation. Okay. So, delta P keeps varying. So, that is why we have different heights here. Okay. So, for under different conditions here. So, 4 things we need to observe here for cutoff, hole distribution, T1 for the normal active, Ts for the beginning of saturation, T2 for the oversaturation. Okay. I hope you understood these things, and let us move on to the next thing here. So, this is the various mechanisms of switching cycle are we have shown now. Device is originally in the cutoff region. A step increase of base current to I B causes the whole distribution to increase approximately as illustrated in the figure 7.15b. Just now we have seen how exactly holes increases as we apply the step waveform of base current at the step waveform nature of base current, okay, at the base terminal here. Okay. So, now let us see the timings here at time T s. T s is nothing but beginning of saturation. The device enters saturation, that is the beginning commencement of saturation, and the whole distribution reaches its final state at T 2. So, we have already shown T 2 state, this is the way the holes reaching the final state of whole distribution at T 2 timing instant. Okay. As the stored charge in the base, this is very important here, stored charge, base, whenever we apply a step waveform like this at the base. So, base will start storing the charges at its the within that region terminal. So, that is what we are trying to say, a stored charge in the base QB. QB is denoted as a stored charge in the base increases when we move from cutoff region to saturation region. There is an increase in the collector current IC. The collector current does not increase beyond its value at the beginning of the TS here. So, we have shown here this with reference to this, when we increase move the base current from cutoff region to saturation region, that means negative 0 or negative value to positive value of base current here. You can observe these two waveforms here. This is the whole distribution, that is stored charge in the base region here for different timing instants you can see here, and corresponding collector current is shown in the below here. So, let us see here now the let me zoom it out, and so you can observe clearly now this timing instance here. So, this is a QB, this is called as a stored charge. So, this is a stored charge graph at base. Okay. So, now when QB is equal to QS, okay, so what happens now here? Let us see that here. You can see that the stored charge in the base keeps increasing. So, now you should also observe this TS. TS is nothing but which is the beginning of saturation. This is BOS, beginning of saturation. When saturation regions commences, we are applying emitter base voltage and collector base voltage is made as 0. So, you can see that when emitter base voltage is applied, suddenly the whole base start collecting the holes and start distributing to the collector. So, therefore, the holes the started the distributing. This is what the phase we are seeing holes has been distributed at the base region here. And observe the collector current here. There is a sharp increase in the collector current here between 0 and TS here. So, 0 means before that you can see here this is the timing here. Prior to that it is a cutoff and you are moving from cutoff to saturation here. So, by applying the emitter base voltage. So, the current starts increasing here, the charges starts increasing, this is a charge graph starts increasing here, and TS is nothing but it is a beginning of saturation. I can observe at this particular time here at the beginning of saturation. So, the you are applied emitter base voltage, and further what it shows is you are also applying along with emitter base voltage the collector base voltage. So, beginning of saturation means it is VEB is applied, but VCB is 0. So, VCB is 0 here. So, beyond this VCB keeps increasing, VCB also we are applying after TS here. So, once you increase the VCB you can see that here now again there is a charges stored charge in the base region keeps increases beyond this QS, and because of increase the base current here, and even collector base voltage also start increasing. At T2 you can see that at T2 is nothing but it is a oversaturated here. Okay, so, that means you have applied both VEB and as well as VCB. So, both are there here, you applied both the voltages, therefore, the device enters into the oversaturation mode. At this point of time when the device is operated in oversaturation, if you suddenly move the apply the negative pulse waveform at the base. So, this is negative pulse waveform applied at the base here. That means, we are moving from saturation region to the collector region. Now, what is going to happen when we move from saturation to the cutoff region here? You expect the immediate withdrawal of charges from the base, but that does not happen. So, because of that you can see that the charges at the base slowly they start it is going to be withdrawn. Okay, so, that is what it is showing. The graph shows that even though you made base current higher value IB to negative value say minus IB here. So, this is a negative value minus IB. So, but the base charges have not become negative. So, it has not become 0. So, slowly the base charges try to become they disappear. So, for between this the peak value of saturation which is happening at T2 to TSD. Okay, so, there is a small gap. You can see that when even though you remove the base current from positive to negative, there is a current collector current does not become 0. So, collector current exists till it crosses the time TST here. Okay. So, till the TST once your the QB stored charge at the base becomes less than the QS, then the collector current is going to become 0 here. So, till that this particular timing instant QB, there is a point at which QB is less than QS. Okay, this is a point here. Once QB becomes less than the QS, then the collector current decreases and the base charges will be removed. Okay. So, that means switching on and switching off it will take its own time. Okay. Even to move to the saturation, it takes its own time, which we are labeled as T1. TS here, that is the commencement of saturation. Saturation to oversaturation we have seen. So, this region is oversaturation, this timing whatever time it takes. So, this is oversaturation. Okay. This region, this is the beginning of saturation, this is oversaturation here. So, collector current is maximum current, collector current is flowing. You can observe here collector current is, there is no significant rise of the collector current is maintained its constant here. But in the beginning when the device is moved from cutoff to saturation, okay, there is a sharp increase in the collector current. So, here you can see there is a sharp increase in IC here. Okay. So, once it reaches maximum, the collector current maintains significantly, it is a constant here, even though the device base current is removed and stored charge start disappearing slowly, but collector current will take its own time. Once QB becomes less than QS, then only the collector current will move towards 0 here. So, these are the various things we have seen here, and let us go through the material here. So, we can approximate saturated collector current as this value. It all depends on saturated collector current, it depends on external battery and as well as RL. ECC is the remote value of the collector circuit battery, RL is the load resistor here, and there is an exponential increase in the value of collector current while QB rises to its value QS at TS. That is what you have seen, collector current raised exponentially. So, this is the graph I am talking now, there is a rise of collector current exponentially, and this rise time serves as one of the limitations of the transistor in a switching application. Okay. We will see that when the collector current rises like this sharply, even we expect this to be immediate, but this offers some delay here. Okay. So, even though it rises exponential, after some time only the rise of collector current will takes place here. Okay. Similarly, when the base current is switched negative, okay, we have seen here when the base current is switched negative from positive to negative here. Okay. So, that is the example, the value of IB is negative, the stored charge must be withdrawn from the base before the cutoff is reached. So, that will not happen immediately, the withdrawal of source charges from the base region. So, that is why the cutoff will be reached very slowly. Even saturation also reached very slowly, saturation and cutoff they are reached very slowly, they are not faster. Okay. And while QB is larger than QS, you can see the graph and you can observe here, when QB is larger than QS, that means you are moving into the oversaturation, right. The collector current remains almost constant, fixed by the battery voltage in the resistor here. Thus, there is a stored storage delay time TSD, what we call, this is storage delay time what we mentioned, TSD. Okay. So, only when this amount of time from this oversaturation to the time at which the QB becomes less than QS, this time is called the TST, storage delay time here. Okay, stored delay time here, TST. Okay, storage delay time TST, after the base current is switched, but base current you have moved from positive to negative and before IC begins to fall towards 0. After TSD you can see that this is a TSD timing instant, collector current keeps falling. Once stored charge is withdrawn, the base current cannot be maintained any longer at its large negative value and must decay to small cutoff value. Okay, this is what we have seen from the this timing graph here. Now, let us see this the switching the transient which includes the delay time here. So, this is a delay time. Okay, this is a delay time TD. Okay, so, this is the transistor switching operations here which is shown with reference to the various timings here. Rise time here you can see that this is the rise time, this time here, this is the time, rise time here, this time total time taken for the output to collector current to rise from 10% of collector current to 90% of collector current here. Okay, so that is called as a rise time here, which is indicated as TR, and opposite to that we have a fall time here, time taken by the collector current to fall from 90% of its value, initial value, to 10% of its value. So, this is the fall time here. Okay. And this is the initial delay time here. We will give reason here why we need to even use this delay time here in our explanation here. So, we can determine the TS, TSD. TS is nothing but the commencement of saturation, TSD is nothing but storage delay time by solving the base time dependent base current equation. This is not under the scope of our syllabus. So, we can obtain the mathematical equation for TS and TSD. For that you need to refer to the chapter 5 okay, on timings related to the BJT. We must not neglect the charging time of the emitter junction capacitance going from cutoff to saturation. There is something a time the emitter junction as is nothing but it is made up of the capacitance. Okay, the depletion region what you have seen Okay. So, one is going to be the emitter and the collector, emitter and the base here. Okay. So, this is emitter junction here. So, this looks like a parallel plate here. So, it needs some time for this capacitor to charge. Okay. So, it requires some time here. So, basically when we in the cutoff region we know that it is reverse biased, all of a sudden we are moving from reverse bias to the forward bias, because we are moving from cutoff to the saturation here. So, this capacitor needs to be charged in opposite direction here. For that it takes its own time, and that is modeled as a delay time here. So, it is necessary for the emitter space charge layer to be charged to the forward bias condition, therefore, collector current can flow. Therefore, we should include a delay time T d to account for this effect here. So, earlier it was cut off, and this was biased in opposite direction. Now, all of a sudden we are moving from cut off to saturation. This charges has to be changed its direction here. For that it needs some time, that is modeled as delay time here. And we already defined rise time and fall time. It is nothing but time taken by the collector current to rise from 10% and to 90% of its final value. Opposite is the fall time here. So, these are the various timings one need to be aware. For this you need to refer to the data sheet given by the manufacturer. So, that will be easier. So, this is shown by the collector current here as a versus the timing is shown with various the delays associated with the BJT here. So, there is a delay time, rise time and the fall time here. So, the definitions are given here also, please look into this for more details. With that, I think we have covered almost all topics with reference to BJT, bipolar junction transistor. If you have any queries, you can ask me, okay, or else we will take some questions during the offline.